Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Celestial Breath, Unveiling the Ever-Changing Symphony of Earth's Atmosphere. The Earth's atmosphere unfolds as a timeless narrative woven through the fabric of our planet's history, its origins and transformations echoing the profound interplay between geological processes and the emergence of life. In the earliest epochs, when the young Earth was a molten sphere battered by cosmic collisions and seething with volcanic fury, the atmosphere was born not as the familiar blend of nitrogen and oxygen but as a transient veil composed largely of water vapor, carbon dioxide, nitrogen, and a host of other gases expelled by relentless volcanic outgassing. During this tumultuous period, the planet's surface was undergoing a dramatic metamorphosis, as cooling allowed the condensation of water vapor into vast, primordial oceans. These liquid expanses began to moderate the raw energy of the early environment, setting in motion chemical interactions that would eventually redefine the nature of the air overhead. In the absence of free oxygen, the early atmosphere was a chemically reducing environment, one that was inhospitable to the life forms that now flourish in oxygen-rich conditions. It was a time when the very elements that would later become indispensable to complex life danced in a delicate equilibrium, influenced by the slow but persistent workings of planetary cooling and the episodic bursts of activity from volcanic vents. The primordial gases, though seemingly inert on the surface, were far from static. They participated in a series of reactions catalyzed by the intense heat and the energy of the early sun's radiation. Over the eons, these reactions contributed to subtle shifts in the chemical character of the atmosphere, gradually steering it away from its initial composition toward a more balanced mixture that could eventually support the advent of biological complexity. A turning point in this ancient chronicle arrived with the emergence of life itself, a development that would irrevocably alter the course of atmospheric evolution. The advent of photosynthetic microorganisms introduced a remarkable agent of change into the planet's chemical dynamics. By harnessing the energy of sunlight to convert carbon dioxide and water into organic compounds, these early life forms released oxygen as an inadvertent byproduct, a process that initiated one of the most significant transformations in Earth's atmospheric history. The gradual accumulation of oxygen, once an inconsequential trace component, set in motion a cascade of chemical reactions that redefined the planet's environmental equilibrium. As oxygen began to build up, it reacted with other elements and compounds in ways that not only stabilized the atmosphere but also paved the way for the evolution of more complex organisms. This critical shift, often described as the Great Oxygenation Event, marked the transition from an atmosphere dominated by reducing gases to one that could support aerobic life, laying the chemical foundation for the biosphere we know today. The interplay between the nascent oceans and the evolving atmosphere was a delicate dance of feedback and transformation. As water vapor condensed and the first rainfalls began to shape the surface, these early interactions influenced the chemical composition of the air in subtle but profound ways. The oceans acted both as a reservoir and a reactive surface, absorbing certain gases and catalyzing reactions that further altered the atmospheric mix. This dynamic relationship underscored a deeper principle, that the Earth's atmosphere was not an isolated shell but a responsive, evolving system intricately linked to the planet's internal and external processes. The primordial exchanges between the hydrosphere and the atmosphere set in motion cycles of chemical renewal that have persisted, in increasingly complex forms, through billions of years. Over vast expanses of geological time, the cumulative impact of volcanic activity, cosmic bombardment, and the metabolic processes of primitive organisms steadily reconfigured the atmospheric envelope. The gradual enrichment of oxygen reshaped not only the chemical character of the air but also the very surface of the planet. Rock formations bear silent testimony to these transformative epochs, recording shifts in mineral composition and sedimentary structures that correlate with periods of atmospheric change. These ancient layers of rock, layered like pages in a history book, offer glimpses into a time when the Earth's atmosphere was in flux, continuously molded by the forces of nature and the relentless march of evolution. Such records have become invaluable to modern scientists, who piece together the narrative of atmospheric transformation through careful analysis of isotopic ratios and mineral deposits, each fragment contributing to a deeper understanding of the conditions that once prevailed on our planet. The metamorphosis from a hostile, volatile mixture to an atmosphere capable of nurturing diverse life forms is a testament to the inherent resilience and adaptability of planetary systems. It is a saga of gradual refinement, in which the interplay between physical processes and biological innovation created a stable and life-supporting environment. The modern composition of the atmosphere, dominated by nitrogen and oxygen with traces of argon, carbon dioxide, and other gases, is not a static endpoint but rather the culmination of billions of years of intricate natural processes. Every molecule present in the air overhead has a story that stretches back to those early, tumultuous moments of Earth's formation, a story of transformation from elemental chaos to a balanced system that supports the delicate web of life. Understanding this primordial evolution offers profound insights into the conditions necessary for life and the factors that govern planetary habitability. The Earth's atmospheric history is a microcosm of cosmic evolution, illustrating how planetary bodies can transition from hostile environments to havens of biological diversity through a complex interplay of internal and external forces. As researchers continue to decode the chemical signatures left behind in ancient rocks and ice cores, they uncover not only the history of our own planet but also clues that may guide the search for life on distant worlds. The delicate balance of gases that characterizes Earth's atmosphere today emerged from a series of gradual, interwoven processes, a reminder that even the most fundamental aspects of a planet's nature are subject to the transformative power of time. In reflecting on these ancient processes, one is struck by the magnitude of the forces at work and the intricate connections that bind the planet's inner workings to the vastness of space. The narrative of the Earth's atmosphere is not merely a chronicle of chemical reactions and physical changes, it is a story of resilience and transformation, one that continues to shape the environment in which life persists. As we stand on the threshold of further explorations into the mysteries of our planetary envelope, the legacy of these primordial epochs remains a potent reminder of the dynamic forces that have, over billions of years, forged a world capable of sustaining the intricate tapestry of life. The modern envelope of air that surrounds our planet reveals itself as a stage where the interplay of solar energy and terrestrial responses generates a ceaseless cascade of physical phenomena. At its very essence, the present-day atmosphere is animated by a continuous dialogue with the sun, whose radiant energy not only warms the Earth's surface but also initiates a complex series of reactions that shape the climate and weather. The incoming light, traversing the vast emptiness of space, encounters molecules and aerosols that scatter and absorb its rays, a process that delicately modulates the energy budget of the planet. This subtle balance between absorption and reflection defines the atmospheric temperature profile, setting in motion convective currents and radiative transfers that perpetually redistribute energy from sunlit expanses to shadowed regions. As the heat is unevenly distributed across the globe, it gives rise to expansive currents that weave their way around continents and oceans alike. Differential heating between the equator and the poles generates vast convective motions, where warm air ascends and cooler air descends in a rhythmic pattern. These rising and falling masses of air coalesce into swirling systems whose dynamics are further refined by the planet's rotation. The deflection of these air streams by the Coriolis force sculpts wide-ranging patterns of circulation, lending structure to phenomena such as trade winds and high-altitude jet streams. In this grand circulation, the atmosphere acts as both a conveyor of thermal energy and a sculptor of weather, continuously forging transient patterns of high and low pressure that dictate the rhythm of storms, calm, and everything in between. Integral to this dynamic tapestry is the ceaseless motion of moisture that imbues the skies with life and variability. As the Earth's surface absorbs solar warmth, water transitions from liquid to vapor, ascending into cooler realms where it condenses into myriad droplets that coalesce into clouds. These ephemeral formations serve as both harbingers of renewal and catalysts of change, releasing latent heat that further energizes atmospheric motions. In their eventual transformation back into rain or snow, these droplets complete an endless cycle of evaporation, condensation, and precipitation. This cycle does more than simply recycle water. It acts as a powerful regulator of thermal energy, ensuring that the atmosphere remains in a state of dynamic equilibrium even as it orchestrates localized episodes of turbulence and calm. In the rarefied heights above the familiar patterns of weather, a different set of interactions unfolds with a quiet yet profound influence. Here, in the realm where the air thins and ultraviolet radiation from the sun is most potent, intricate processes conspire to protect life below. High-energy photons encounter a region where molecular interactions absorb and diffuse their potential harm, giving rise to a protective barrier that moderates the influx of damaging radiation. This shield not only safeguards biological systems but also establishes a thermal structure that influences the transfer of energy between layers. In these upper altitudes, the delicate equilibrium between radiative heating and cooling steers the overall circulation, creating gradients that extend their influence from the edge of space to the surface below. The convergence of these processes is nowhere more apparent than in the intricate interplay of regional weather systems, where localized disturbances arise from subtle imbalances in temperature and pressure. Here, the broad strokes of global circulation intersect with the finer details of transient atmospheric eddies. Regions of high pressure, where the air settles into a state of relative calm, often lie adjacent to turbulent zones where opposing air masses collide. In these zones of contact, the tension between warmth and coolness intensifies, triggering bursts of convective activity that can evolve into formidable storms. The complexity of these interactions underscores the atmosphere's sensitivity to minute variations, where slight shifts in thermal energy or moisture content may cascade into dramatic climatic events that reshape local landscapes and influence broader weather patterns. In recent times, the delicate equilibrium of these natural processes has encountered a new and potent influence. Human activity has introduced perturbations that resonate throughout the atmospheric system, subtly altering the interplay of energy, moisture, and momentum that had long defined the planet's climatic rhythm. The addition of industrial byproducts and alterations in land use have modified the balance of radiative forcing, prompting shifts in temperature gradients and the dynamics of moisture transport. These anthropogenic influences, while emerging within a framework honed over eons of natural evolution, now participate in the continuous dialogue that governs atmospheric behavior. Their presence is a reminder that even a system as vast and seemingly immutable as the air above is in constant flux, susceptible to both the grand forces of nature and the deliberate actions of its inhabitants. In the ongoing quest to decipher the intricacies of our planet's gaseous shroud, recent advances in observational techniques and computational modeling have unveiled layers of complexity previously hidden from view. Modern instruments, orbiting satellites, and sophisticated ground-based remote sensing systems have converged to offer a window into the subtle interactions that govern the behavior of trace constituents and fine particulates. These innovations have allowed scientists to peer into the microscopic realm of atmospheric chemistry, where fleeting radicals and minuscule aerosol particles engage in reactions that govern radiative transfer and determine the delicate balance of energy across the globe. This refined understanding, achieved through a confluence of spectroscopy, LiDAR measurements, and advanced data assimilation techniques, has transformed our capacity to monitor the atmosphere in real time and predict its response to both natural and human-induced perturbations. At the heart of this refined perspective lies a detailed appreciation for the chemical dance that unfolds on scales invisible to the naked eye. In the thin margins of the atmosphere, where concentrations of reactive gases exist in parts per billion, complex cycles operate with profound implications for climate stability and environmental health. Molecules such as methane, nitrous oxide, and a host of volatile organic compounds engage in interactions that not only modulate the absorption and emission of thermal energy but also drive feedback mechanisms that ripple through the system. The nuanced interplay of these trace gases, combined with transient species formed in situ under the influence of solar radiation, has redefined our understanding of radiative forcing. As research continues to elucidate the kinetics of these reactions and the role of heterogeneous processes on aerosol surfaces, a clearer picture emerges of an atmosphere that is as much a chemical reactor as it is a dynamic fluid enveloping the planet. A further dimension of atmospheric inquiry has emerged from the study of the protective and transformative layers that interface with space itself. In the ionized regions high above the familiar blue canopy, charged particles and electromagnetic forces combine to create an arena where terrestrial and extraterrestrial influences intermingle. The ionosphere, a region characterized by the interplay of solar wind particles and the Earth's magnetic field, is a testament to the atmosphere's capacity to act as a mediator between the planetary surface and the broader cosmos. Detailed investigations into this region have revealed its profound impact on modern technology, affecting radio signal propagation, satellite communications, and the reliability of navigation systems. As research in space weather deepens, the understanding of these high-altitude processes not only safeguards critical technological infrastructure but also offers insights into the universal principles governing planetary envelopes throughout the cosmos. In parallel with these advances in fundamental science, the translation of atmospheric research into practical applications has yielded benefits that extend far beyond the laboratory. The integration of high-resolution modeling with expansive observational datasets has sharpened the accuracy of predictive systems, enabling more effective early warning mechanisms for environmental hazards and informing strategies for sustainable management of natural resources. This fusion of empirical science with computational prowess has also spurred the development of interdisciplinary approaches that link atmospheric dynamics with terrestrial and aquatic ecosystems. In doing so, researchers have begun to unravel the intricate feedback loops that connect the chemical composition of the air with soil processes, ocean circulation, and even the health of human populations. Such insights have catalyzed policy frameworks designed to mitigate adverse impacts, illustrating how a deepened understanding of atmospheric processes can be harnessed to promote resilience and adaptive capacity in the face of global change. Looking forward, the study of Earth's atmospheric system stands at the confluence of tradition and innovation, where long-established physical principles meet the transformative potential of emerging technologies. New computational paradigms, including machine learning and high-performance simulation techniques, are poised to unlock further secrets of a system that remains both ordered and capricious. These efforts are complemented by international collaborations that pool expertise and resources in an era when the planet's environmental challenges are increasingly interconnected. As scientists push the boundaries of what is known, the atmosphere continues to reveal itself as a dynamic interface, an ever-changing boundary where the laws of physics, chemistry, and biology converge. In this evolving narrative, every advancement in observational capability and every breakthrough in theoretical insight serves as a reminder of humanity's enduring commitment to understanding the natural world, ensuring that our stewardship of the planet remains informed by the most comprehensive and nuanced knowledge available.